Hello and welcome. In this screencast, we will quickly review the range of the inverse sine, cosine, and tangent functions before moving on to find some missing angles in the coordinate plane. Previously, we saw that the range of the arc cosine function is 0 to pi inclusive, which means any time we use a computational device to evaluate the arc cosine function, the output will be angles in quadrant 1 or quadrant 2. The range of the arc sine and arc tangent functions is negative pi over 2 to pi over 2 inclusive, which means any time we use a computational device to evaluate the arc sine or arc tangent functions, the outputs will be angles in quadrant 1 or quadrant 4, where the angles in quadrant 4 are represented as angles traveling clockwise around the unit circle. There are a handful of values of the inverse trig functions we can find exactly. For example, we know that from the unit circle and the range of the arc sine function, that arc sine of negative 1/2 will be in quadrant 4, whose sine is negative 1/2. This happens to be 11 pi over 6, but we represent that as negative pi over 6 because we represent it as an angle traveling clockwise around the unit circle. Similarly, we know from the unit circle and the range of the arc cosine function that the arc cosine of negative 1/2 will be an angle in quadrant 2, whose cosine value is negative 1/2, and that happens to be 2 pi over 3. There are many other values we may wish to know that are not one of the special points on the unit circle. So in the next examples, we'll learn how to find missing angles in the coordinate plane that are not any of the special points on the unit circle. So example 1, consider a right triangle with legs of lengths 5 and 7. Draw a picture of the situation and then determine the exact and approximate measures of the non-right angles in radians and the length of the hypotenuse. Pause the video and try to set this up on your own. Okay, so we're going to go ahead and draw a triangle here whose legs are 5 and 7. I think my vertical leg looks a little smaller, so we'll label that 5. I'm going to go ahead and label this top angle alpha and this lower angle beta. So if we wanted to find angle alpha, we have the opposite side and the adjacent side. So we could say the tangent of alpha equals 7 over 5, opposite over adjacent. And then using the inverse, so the arctan, the input and output will reverse. So we'll have the arctan of 7/5 equals alpha. And that is the exact value for angle alpha. And if you use a computational device, you would see that in radians, alpha is approximately 0.9505 radians. All right, next we could find angle beta. There's two ways we could do that. We could set up a tangent function again because we have the opposite side, which is 5, and the adjacent side, which is 7. So using inverses, we could say arctan or inverse tangent of 5/7 equals beta. Again, that's the exact answer. And then using a computational device, you would see that beta is approximately 0.6202 radians. Alternatively, another way to find beta would be to recognize that alpha plus beta would have to add up to 90 degrees, which in radians is pi over 2. So beta would equal pi over 2 minus alpha, and we knew alpha was the arctangent of 7/5. So that could be an alternative form for the exact value for beta. All right, to find the hypotenuse, we could go ahead and use the Pythagorean theorem. 7 squared plus 5 squared equals the hypotenuse, h squared. And I'll let you finish that on your own. I want to look at one more example here. All right, so it says consider an angle theta in standard position for which we know the cosine of theta equals -4/10, and theta is in quadrant 3. Draw a picture of the situation and then determine the exact and approximate measures of theta in radians. In addition, what is the exact and approximate value of sine of theta? I would pause the video, try to draw the picture, and see how far you can get. Okay, so we got to be careful on this one. We know that theta is in quadrant 3. So I just want to remind you, this is theta, that whole angle there. And we could draw a right triangle. We know the cosine is -0.4, so that would be the x-coordinate, which means I know that leg is -0.4. And we're trying to find theta. So we can go ahead and start out by thinking of the inverse cosine of -0.4 equals theta. But keep in mind, that's actually not going to be true because the inverse cosine only gives us values in the quadrant 1 and quadrant 2, and theta is in quadrant 3. So we're going to have to do a little bit of work here. The inverse cosine of -0.4 is actually going to give us the angle in the second quadrant that would produce the same x value, which is fine. But we're just going to have to keep in mind that we haven't found theta yet. We're going to find this other angle I'll call alpha. So if you were to use your computational device, you'll see that that angle in the second quadrant is approximately 1.98 radians. And here's another way that might help you think about it. We know that pi over 2 is here on the positive y-axis, and if you were to get a decimal approximation for that, it's about 1.57, and we know pi is over here on the negative x-axis, which is approximately 3.14. So if we think about this, 1.98 radians is going to be somewhere between 1.57 and 3.14 radians. So just another way to realize that when we did the inverse cosine of -0.4, it gave us an angle in quadrant 2. And so we want an angle in quadrant 3. So what we can recognize is that if we go counterclockwise, then that would be negative alpha. And we could think about rotating all the way around the circle, 2 pi, and then backing up alpha. So that would get us where we really want to be. So ultimately, the angle theta we're looking for is 2 pi minus this angle alpha we found, which was the inverse cosine of -0.4. So that would be our exact answer for theta. And then you could use your computational device and see that theta is approximately 4.30087 radians. And again, 4.3, that's bigger than 3.14, so that makes us a little comfortable that we're probably in the third quadrant there. All right, lastly, in this problem we were asked, what is the exact value and the approximate value for the sine of theta? Well, if we know what theta is, then there's a couple of ways we could do this. We could say that the sine of theta is going to be the sine of, and then we would just substitute in what we found, 2 pi minus the inverse cosine of -0.4. Or we could also recognize we have a right triangle, and we know one of the legs is 0.4. We're looking for the y value to find the sine of theta, and we could assume here, since the leg is smaller than 1, we could assume that we're in the unit circle. We're just not on one of the special points, so the radius is 1. And so we would get y squared equals 1 squared minus negative 0.4 squared, we would take the square root, and typically we have that plus or minus the square root. And keep in mind in this case, because our angle theta is in the third quadrant, the y values are negative there. So our exact value for y would be the negative square root of 1 minus negative 0.4 squared, which would be 0.84 in our square root, and that would be approximately negative 0.9165 for our y value.